Alright, 130 students. Try this test of me creating videos and then using class time to work through homework problems. So we're going to look at our first video here is section 3.8 from cluster 2. We're talking about logarithmic functions. I'm a big Lego fanatic. So here's a Tusken Raider from Star Wars in Lego. Okay, so let's get started here. Our goal for this section, is to figure out what's up with logarithmic and exponential forms of expressions. So we're going to start here with a contextualized problems, this idea of spheres. They're all around you. Pardon the pun, haha, I guess. That's funny. And here is the formula for a sphere. The volume of a sphere is 4/3 times pi, that constant 3.14 times r cubed. And then the surface area is this 4 pi r squared, where r is that radius from the sphere. And you can think about this radius going anywhere from that center of this three-dimensional object to any point on the surface. So the thing is that not all of these spheres are the same size. And this is the diameter, this table, of some of the spheres we know: a golf ball, a baseball, basketball, the moon, the earth, and Jupiter. Now, if you don't remember what diameter is, it's twice the radius, so it's this full distance. So these are, if you look at the diameters of these different spheres, they're drastically different, right? These are in what, meters? So a golf ball, 0.043 meters, and then a baseball, 0.075, and then the moon, 3,476,000, and Earth, 12 million, whatever. So our textbook author says, hey, let's try to graph these. Well, I shouldn't say graph. Let's plot these things on a number line. And we're told to plot the first three. So here goes. I'm going to do this. We're told to use a scale of 0.02 meters. So I guess I'll put 0 here. And this would be 0.02, 0.04, 0.06, 0.08. I don't really want to plot all three. I'm just going to plot those first two. So 0.043, let's see. The 3, if we broke this into tick marks of 10, we could do 1, 2, 3. There's clearly not tick marks of 10. So we'll just estimate 0.043 to be right there. And then 0.075, that one is going to be exactly halfway between no. If this was 0.07, it would be halfway between those two. That's where that one would go. And then the 2.39 is going to be somewhere over here. Let's just pretend it's that. Okay, and then the author's like, all right, now can you plot all the values? So I apologize, I only have a textbook with an answer key, so that's why I'm having to cover this up. So there's how the textbook's answer looked. Yeah, it's close to mine, right? Yours is probably better. All right, so now can we plot all of them on there? Well, if this is my ending of 0.239 and I'm trying to get to 3 million with tick marks, like even this is probably, even going all the way over here is probably not even getting to 1. And I got to get to 3 million at tick marks of 2. So is that possible? No. This scale is way too small. I'm going to run out of paper. Ugh. All right, then the textbook's like, well, let's plot the values of the last 3 rows on a different axis with the scale starting at 0 and then increments of 10 million. Well, then we can plot those 3 values pretty easily and get a rough idea, a visual of how far apart these numbers are. So the point here is there should be a way that we can put these all together, all 3 of them together, to get a nice picture of that data set. So those varying diameters. This question, of course, the scale is too big to put in those 0.043 values, just way too big. So turns out there's a nice way to scale an axis where we can have both large and small numbers on it and have a relative sense of how far apart are those numbers. So let me demonstrate how they got that answer that you were seeing. We're going to start with the leftmost tick mark and give that the value of 0.01 meters. Now, if you recall scientific notation back from your project, we could write this in scientific notation by dividing by 100, as is what is noted here. And that has the effect of moving the decimal place 2 places to the right. And we would write this as 1 times 10 to the negative 2, since we divided by 100. And since this is a 1, we don't need all this part, so we could just write this as 10 to the negative 2. So then the next tick mark, if we make that the value of 0.1, notice we have essentially multiplied this value by 10, so we would actually call that 10 to the negative 1. And then the next tick mark would be 1. By the way, notice 0 is like over here, somewhere over there. So to get a 1 in scientific notation, we'd write that as 10 to the 0. Okay, so now I'm going to rewrite this following their strategy here with the exponential or the scientific notation. So 10 to the negative 2, 10 to the negative 1, 10 to the 0, 10 to the 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So let's think about in non-scientific notation, what's up with this number? How big is it? Well, that's a 1 with 5 zeros after it. Does that seem right? 1, 2, 3, 4, 5. Yep, 10 to the 5th. So we're at 100,000. When we hit 10 to the 6th, we're then now, if we're writing this in decimal form or standard form, we're now at 1 million. So if you think back to those numbers, we're getting close to what we would need for our scale to have both small numbers on one end and large numbers on the other. So this is 10 million at the 7 mark, and then at the 8, it's 100 million. And thus we get the picture that has been given to us here that is in my answer key. We get a nice, what's called a logarithmic scale, meaning we have our tick marks in multiples of 10, and we can graph all of these values. We can plot these values on that axis quite nicely. So 0.043 is somewhere between 10 to the negative 2 and 10 to the negative 1, closer to 10 to the negative 2 than negative 1. And 0.075 is between those same two values. 0.239 is larger than 0.1 but smaller than 1, and so on and so forth. And now we have a visual representation of the different diameters, sizes of diameters of this thing. So the next task for us in our textbook is to fill in this table in scientific notation. And that might actually help us better understand how did our authors, when they gave us this answer, or gave me this answer, how did they plot these values in here? So recall that to get scientific notation, we need a number in the form of a times 10 to the n, where a is a value between 1 and 10, and it cannot equal 10, but it can equal 1, and n has to be an integer, meaning negative 3, negative 2, negative 1, 0, 1, 2, 3, all that. So I know that this needs to become 4.3 for it to be a number between 1 and 10. And if you think about what happened, if I want to turn this into 4.3, I have to actually multiply it by 100. So to undo that, I have to write it as 4.3 times 10 to the negative 2. And I'll go through the rest. I think you all are pretty good at doing scientific notation. There's my cat. 10 to the negative 1 here. And then this one, 3.476 times 10 to the, these would be positive, and I can just count the zeros. 1, 2, 3, 4, 5, 6. And then be careful, I almost wrote 12.756, but this number needs to be between 1 and 10, so it's got to be 1.756. And that would be times 10 to the, we just added one more from here, right? So that would be a 7. And then 1.42984. I'm going to count this one just so I don't mess up. 1, 2, 3, 4, 5, 6, 7, 8 times 10 to the 8. All right, now we've got those all in scientific notation. And then you can see that when we're plotting these up here in this scale, 4.3 times 10 to the negative 2 is between that 10 to the negative 2 and 10 to the negative 1. And it's a little closer on this end than that end.